improving computational methods for designing polar protein-protein interfaces. And I'm going to start at the very beginning of what is a protein. Proteins are these long polymers, meaning that they are linear chains of repeating units. For proteins, the unit that's being repeated is an amino acid. We also call these residues or positions of the protein. When you create this chain of amino acids, we call this the main chain or the backbone of the protein. And then branching off of this main chain, there are side chains. We'll also use the term rotamer to refer to these side chains later. And these can be more diverse. Nature has 20 different possible side chain chemistries that you can choose from when building up a protein. The ordering of these amino acids is called the protein sequence, and that sequence is sufficient to define the protein. We visualize proteins like this, where the main chain is, you just view using thick shapes like this ribbon, and then only the side chains, you see the individual atoms. And this illustrates how the main chain itself is not rigid, it's flexible, and a common shape you see is for it to fold into this helix that you see along the left side. Proteins can interact with each other, two can come into contact and create an interface, which is the point of contact between the two chains. The interface is dictated by the side chains generally. This can be useful for any number of purposes. So there's enzyme activity. You can catalyze reactions by bringing proteins together and creating a chemical region in space, or you can inhibit proteins. You can tag molecules by creating binders for them, and that can be used for all sorts of purposes. And it's really up to the creativity of the biochemist. This is really more of a tool that you can use for many purposes. So our lab, like Brian mentioned, is part of this community of labs across the world that all contribute to this Rosetta protein modeling software. So Rosetta is a hypothesis generator in the sense that you might have a situation where there's a protein sequence and you only know the sequence of amino acids that create the protein, but you don't know the shape that it folds to in nature. So you can give Rosetta a sequence, and then it will give you some hypothesis of what structure that sequence folds to. Or the opposite, if you would like to create a protein, and you can choose what sequence creates it, you can create, and you have some fold that you want the sequence to fold to, some structure, you can ask Rosetta to give you some hypothesis of what sequence will fold to this shape. You can do more advanced things, such as, maybe you have a bunch of candidate protein sequences and you want to model which one is most likely to do any of the things I mentioned on the previous slide, like catalyze this reaction or bind to this native target. And Rosetta can model these candidates. But really the point I'm trying to get at is, even though Rosetta does not directly replace lab work, it can reduce the work that humans have to do by decreasing the hypothesis space and what sequences you are considering for whatever role that you are modeling in your job. The mechanics of this process is this score function in Rosetta, where Rosetta will simultaneously consider the structure of a protein and its sequence and assign the marriage of those two some sort of energy or score. And you can use this in two ways. One is prediction, where experimentally or in some manner you might have a sequence of a protein and you don't know what it looks like in space. You can just give Rosetta the sequence that you have, and then Rosetta will sample different conformations and optimize the score. The conformation that gives the best score is Rosetta's predicted folding pattern for that sequence. The opposite is design. So that's if you have, for your own reasons, you have some shape that you want to design a protein to fold to. You can give that conformation to Rosetta, and it will optimize the score by sampling in sequence space, and then whatever sequence gives you the best score is the hypothesis design of the sequence that you end up testing. It can get more complicated than that. So imagine if you set out to design this interface. Perhaps in this example, there's this green protein that is this native protein that you'd like to bind to, and in blue you want to create some other protein chain that comes in and binds to it. You're not allowed to change the sequence of the native protein, but you can pick whatever sequence you want for your own design protein. So this is more advanced than my previous example because Rosetta needs to model a sequence that not only folds to the shape that you want, but also optimizes the sequence for those sidechain interactions across the interface. And this is where the challenge that I'm going to talk about today is introduced. So when you design an interface, some of these sidechains have polar atoms, and all of these polar atoms are going to need hydrogen bonding partners. So for example, in this native protein in green, if there's this hydroxyl that is buried by the interface, when you're in the unbound state and the chains are apart, that hydroxyl is interacting with water, and you have to break those hydrogen bonds with water in order to build the interface. And if you don't have some other hydrogen bonding interaction to make up for that lost water interaction, there's a loss of binding. There's a desolvation penalty. So you need hydrogen bonding partners for all of the native polar atoms, and the reverse is true too. You can't introduce polar atoms on the side that you can control without giving them hydrogen bonding partners for the same energy penalty. But this case is a little bit more nuanced because since you're controlling the sequence of the protein, you can imagine that you can just change the sequence so that there's no polar atom there, and then it's easy to fix. But it's not that easy. You need a minimum amount of polar atoms at your interface because in the unbound state, especially for proteins that are transient and will be bound and unbound off and on, that side of the protein is going to be exposed to water. And you need polar atoms, otherwise you get this oil and water effect, and your protein will just not be soluble. So you need a minimum number of polar atoms to be soluble, but all of them need hydrogen bonding partners. Now, a few years ago, a former student of the lab, Ben Stranges, studied all of the recent protein-protein interfaces that were designed with Rosetta and then were later tested in the lab. And he wanted to look for patterns on which designs failed and which succeeded. And one of his primary conclusions is that Rosetta could not meet the two restrictions that I mentioned before. It could not design enough polar atoms and find hydrogen bonding partners for them consistently. So I included this snippet from his conclusion, which has two calls to action. His first is a conclusion that Rosetta just isn't modeling physics well enough with regard to this. There needs to be an improvement in how hydrogen bonds are analyzed and scored, and also how desolvation energies are just modeled and scored. Rosetta needs to be able to be better at knowing when atoms can hydrogen bond with water and when they can't, and then when they have a good hydrogen bond with another protein and when they can't. So that's the first call to action in green. That's a scoring improvement. The second is what we'll be talking about today, and that's sampling. He said that, Rosetta might not be able to find all of its opportunities to create hydrogen bonding interactions. There might be an opportunity to create a mutation on the side, on the protein chain that you can change the sequence for. There might be an opportunity to change the sequence in order to create a hydrogen bonding interaction, but Rosetta just can't find it. And so not only does scoring need to be improved, but sampling needs to be improved. So this is a timeline of all major Rosetta developments since that paper came out. And I split it into the first call to action of scoring and sampling on the bottom. There's been plenty of work on improving scoring, not so much with sampling. And even it turns out that the two on the sampling side that have been made, we'll talk a little bit about today. are insufficient. Like they alone are not enough to improve interface design. So the goal of my project is to add more to the sampling side of this timeline and introduce more ways to improve hydrogen bonding sampling. So just to summarize up to this point, there are cases where designed to interface proteins need to have polar atoms, but these polar atoms need hydrogen bonding partners in the bound state. So those are two restrictions, and Rosetta, as of that study a few years ago, is unable to consistently satisfy both of those two requirements for two reasons: scoring and sampling. Scoring's been worked on. As far as we can tell, it's improving, and there's plenty of work going into that. Sampling still needs to be improved, and that is today's goal. So just to outline what I'm going to talk about, I want to do a quick review of the status quo, how Rosetta samples sidechains when designing interfaces. And I'd like to discuss two implementations of improvements that we've made in the past few years. And then finally, I'd like to close off with benchmarks that show that these improvements actually improve hydrogen bonding sampling. So it'll be a little bit, it might feel out of order because I'm going to talk about implementations without going into detail of how they improve everything until the very end, where I show them together, how everything improves together. But first, just to review how Rosetta samples sidechains. The sidechains themselves are flexible just like the backbone. However, they're predictably flexible. They have fewer degrees of freedom, and we have enough data on like crystal structures of proteins to be able to group different sidechain conformations and cluster them and just sample them discretely. So what I'm showing here on the left is an example of a cysteine sidechain being sampled, and this is looping, but there's really only 6 different conformations we're looping between. And Rosetta, when it samples what the conformation of that sidechain will be, it just builds this set of rotamers, meaning that we use rotamers to just mean alternative sidechain conformations. We'll build this rotamer set for every position. And it's a small number for small sidechains like cysteine. And the set grows for things like arginine because they're more flexible, so larger sidechains will have a larger set of candidate states at each position. But these are all discrete sampling. You just an array of conformations that can be chosen between. This is where it gets a little bit messy, but when you have this whole chain and you want to predict all of the sidechain conformations for the chain, you have to build all of these rotamer sets for each position. And then the way Rosetta makes its prediction on sidechain conformation is it just gives random assignments for every position, and then stochastically changes, just makes changes for, it'll just pick a position and then pick a different state for that position. If the change in state improves that Rosetta score that I mentioned, then that's accepted. And even if it's a change for the worse, it's still conditionally accepted based on probabilities. Sometimes you need to become less favorable in order to reach a lower energy well. And so, especially early on, Rosetta will allow changes for the worse with the expectation that you'll get that back later, and it'll be for the greater good. This gets even more complicated for protein sequence design. When you're trying to optimize a protein sequence, it's the exact same thing as what just happened. The main change is that a single rotamer set or sidechain conformation library for each position actually spans multiple amino acids. So I know it's kind of hard to see in this video, but when these changes are being made, I think this video stopped. When changes are being made, mutations can be introduced, and the set of candidate states at each position is not just confined to one amino acid. You can change the chemistry of a position as you sample these sidechain conformations. even though you change the chemistry, we still use the term rotamer. It's turning into jargon because it's no longer chemically correct because they vary more than just by torsion angle changes. But rotamer is still the term that we use just for candidate side chain conformation. Chemically speaking, from a physical perspective, it might seem odd that you can just introduce atoms or remove atoms. That chemical equation is not balanced. And the way Rosetta handles this is with reference energies. Each amino acid has a baseline energy, which is considered when making mutations. So you'll measure the change in Rosetta score, and part of that change in score will include how the baseline energies of each position changes. That's Rosetta's way of, it doesn't model physics directly, but it handles that. It tries to make mutations in apples-to-apples comparison within the scope of the Rosetta score. What I'd like to talk about now is fast design, and this is Rosetta's premier flagship sequence optimization protocol. So if you consider what I just showed, that a single run of this rotamer substitution where you just randomly sample different side chain conformations, just visually, if that's this blue box here, fast design will run this 20 times in a row where the output of one rotamer substitution call is fed into the next one. We also call these packing steps rotamer packing, just to expand the jargon, because that probably will fall into that. And in between each call to this rotamer packer, there's a step of gradient-based energy minimization, which is a big title of saying we allow the backbone to move a little bit, right? In rotamer substitution, the backbone is completely fixed, and that's partially because it just makes the rotamer substitution case simpler if you just assume a fixed backbone. However, you can imagine that a mutation from a small to a large side chain or the opposite. It might be favorable, but it might be even more favorable if you allow the backbone to make small perturbations and maybe twist in such a way to make room and allow all the side chains together to pack together. So we want to allow that. So this is an exaggeration of how much the backbone moves, but just to show it's just steps of minute backbone adjustment. There's this extra parameter, which is a chunk of this project that we'll be diving into, which is this repulsive weight ramping, which I'll describe in a second, but just to give the idea of it first, you can imagine that you're in this energy well, and there's this lower energy well that you want to enter, but there's this energy barrier in the way. The goal of this ramping system that we have is to periodically lower the energy barrier and then slowly scale it back up. And that allows us to just kind of tunnel into other energy wells, but periodically reminding ourselves what our best model of physics is supposed to look like. Now, this term that is being ramped itself is the Leonard-Jones repulsive weight, and that essentially models how close atoms want to be to one another. Essentially, we're allowing, when we lower that barrier, we're allowing more atoms to fit in a small space without a large penalty. And as we increase that, we try to more closely model in real physics how close do these atoms want to be to one another. Now, if I take a closer dive at this y-axis of this repulsive weight, as you move up this weight, you introduce what I'm calling, for the scope of this talk, steric debt. And that's the concept that the score function itself is becoming less forgiving. A set of atomic distances that used to be acceptable are now considered clashes. And as the score function becomes less forgiving, you need to start resolving these clashes of these atoms being too many atoms in a short confined space, or just any set of atoms are too close to one another. The opposite, as you go down the axis, the score function is more forgiving, so you're welcome to move atoms closer together and have more atoms in a confined space. So we have these two states, steric debt, steric surplus, And these two sampling methods, rotamer sampling, or the Packer, and then this backbone adjustment, minimization. And both sampling methods handle these two conditions differently. When you're rotamer sampling, you can't move the backbone, you can't really make small changes. All you can do is make like sweeping conformational changes in the side chain or mutate the amino acid. So if you have steric det, then you have too many atoms in a confined space. And so more often than not, what the rotamer sampler has to do is mutate to smaller side chains to decrease, to just resolve those clashes that used to be acceptable, but now they're not. So we get rid of them. In steric surplus, you get the opposite. You have more freedom to fit atoms in a small space. So you see mutations to large side chains. With minimization, you can't make sweeping changes. You can't make mutations. All you can really do is just slowly allow atoms to move away from each other. So if you have steric det and you need to resolve these clashes, your protein will actually slightly increase in volume because these atoms, which used to be at an acceptable distance, are, they realize they need to be farther apart. So everything, the volume of the protein increases a bit. And then the opposite happens. If you're allowed to pack atoms more closely, the protein decreases in size and atoms shrink inward toward the middle of the protein. I know that's a lot, but that'll come in a second. While we look more closely at a single sawtooth of this fast design shape, it's not a pure diagonal for the repulsive weight. It's a stepwise increase. There's this initial steric surplus. I'm labeling each section for it. So we have the Packer and the minimizer. So they're either going to be under surplus or det. And initially you drop from a normal, our best model of physics score function, you drop to be very forgiving. So that's the definition of the surplus that I'm defining. Now the rotamer substitution, the blue step, it makes sweeping changes, and so it won't. It's really discrete sampling of the score function, and it won't be able to use all of this surplus. The analogy is like it won't give exact change if the surplus is if it's like $12.34, it will only pay in the full dollar amount. So it'll leave some surplus for the minimizer, which will use the full amount available to it. And then we're going to start moving our way back up this y-axis and introducing steric det until we pay off what was originally given at the beginning. The Packer, for the same reason that there's surplus left over for the minimizer here, the Packer will likely not have exact change, so it will likely overpay by a hair and leave a small surplus for the minimizer. And that will happen with every step increase. So surplus, surplus for both, then det surplus, det surplus, det surplus. And you get this imbalance. So if you count up this score sheet, more often than not, we're mutating to small side chains. But there are opportunities to undo that. At the beginning of each sawtooth, there's an opportunity to mutate to a large side chain. So this might even out. The big problem is on the right. There's this unbalanced sampling bias. Every time you run the minimizer, if there's an incentive, if there's a sampling bias, it's towards the protein decreasing in volume, and you never have the opportunity to have the other sampling bias to even that out. And really that's what I see. So I benchmarked this case, and I've run fast design on many proteins, and what I find is that there's this unbalanced trend to mutate towards small amino acids, most commonly alanine, in which the side chain is just a single carbon. In partnership with the backbone moving in, in partnership with these mutations to alanine, the backbone of the protein shrinks inwards. The radius of gyration is a metric that measures roughly how much, at least in the way that we're using here, it roughly measures how much space, how large the protein is, how much space it's taking up, and that's decreasing to 97% of how it starts at the beginning of fast design. 97% sounds a lot like 100%, so that's not a huge red flag. But it is the reason for the first problem, and that's the big problem. This sampling bias in the mutations is a large problem, and it's caused by this imbalance in sampling bias. This occurs at protein cores, so if you just run a single protein chain, that chain will decrease in size and mutate alanine in the middle, in the part that is not solvent exposed. And relevant to this talk, it happens at protein interfaces. Residue positions at the interface of two chains will have this bias towards sampling, mutating to alanine, and then the two chains actually move closer to each other in space. And the reason this is relevant is that it's very hard to find hydrogen bonding partners for your polar atoms if all of the other residues are trying to become alanine. And just in general, the polar amino acids have larger side chains. So if there's any sampling bias towards small side chains, this is really going to make things difficult for us. And that is what we find. So this is abstract. I'm going to move a little bit back towards what this looks like in the protein. This is an example of a case I benchmarked. This is a single protein chain, about 100 residues. And the innermost, least solvent-exposed residues, I've written the sequence on the right. And what's shown here is before Rosetta's touched it at all. These are the amino acids that are at those core positions. And after this first stage of surplus in the packer, you get sort of what I mentioned before, where you have this opportunity to mutate to all of these large side chains. So in green, I'm showing mutations where the number of atoms at that position has increased, mutations where the side chain gets larger, and then in red, only at one position does the side chain actually decrease in size. So because of this steric surplus in the packer, we get these mutations to large side chains. But then once you start introducing that, you get the opposite, and it overshoots where you started. These colors are relevant to the original sequence, and half of the protein core is smaller than where we started just after this first packer call that's under det. And this never really recovers so much. Just one of them really came back to the original size. So by the end of this, this protein is it's smaller. So I'm exaggerating, but I'm showing the concept that I mean, where the atoms shrink towards the inner part of the protein. And there are these mutations that seem to be introduced in, what seems to be an irreversible way. So we set out to fix this, and this is just a different way of visualizing the same ramping scheme that I had on the previous slide. So the y-axis is the same repulsive weight. The colors are the same for the rotamer sampling protocol and the minimizer. And I actually have the actual numbers of what the repulsive weight is, in which a weight of 1 is the weight that best models physics within Rosetta's system. It's the best attempt to model real physics, and then as this number gets closer to 0, the score function is more forgiving. So same scheme, and then we really want to keep these last two numbers at 1 because we want to finish each of those sawtooth patterns with our best attempt to model physics, but there are still 6 values that we want to try and fit to get rid of this sampling bias. So, the naive thing to do is just do a 6-dimensional grid search where you allow each of these 6 properties to vary independently, run Rosetta with that set of properties, see what the output is. That's very expensive. It's high dimensional with 6 degrees of freedom, but also we want to test this on a large, diverse set of proteins. So we need to run a lot of Rosetta tests to test each parameter set. So we deemed that was too expensive. This is how we decreased it to 2 dimensions. The first is interpolates the weight of the minimizer steps between the 2 neighboring packing steps. the idea with this is that, after every packing step, there's a little bit of that steric surplus left over for the minimizer, and this is just attempting to cancel that out. The other way is a little simpler. It's just decreasing that initial surplus given at the beginning and just adding this floor to the entire system. So we did a two-dimensional grid search of those two properties. So this y-axis is the interpolation, which I call lambda, which varies from 0 to 1, where 1 is it's fully the next packing step's weight and 0 is the previous. And then the other property is floor, so that's just the value that's added to every step across the board. Same range, 0 to 1. We did two different design cases. The top is when you just have a single protein chain in space and you want to optimize the sequence for that chain. The bottom is really more on topic for this talk. That's where you have two proteins in contact and you're just allowing the residues at the interface of those two proteins to optimize their sequence. Now the values in the table are the average Rosetta energies per residue, and we don't need to interpret them directly. For this slide, all we need to know is that lower, more negative is better, and I've color-coded it such that green is better. At a glance, it looks like these two heat maps are a little bit different, but really for both of them, once you leave the 0, 0 corner, which is the status quo if we don't change anything, once you leave that corner, it's pretty flat here. So there's somewhat consensus. And really what we found is both of those individual degrees of freedom, when you sample them independently, they both improve the situation. But our best results are when you sample together. The best points are where you add a little bit of a floor and a little bit of interpolation. Just to give you an idea of what that looks like, I've highlighted this one of these well-performing cells. The parameter set for these cells looks like this. So it's really only a slight increase in weight for the minimizer. There's only a little bit of surplus that we had to cancel out. And this floor doesn't look very large at a glance, but if you look at the first few steps, we're almost tripling that initial weight of the first packing step. So this is one of the winning combinations of what needed to be changed. So just to summarize our results for fast design, I spent 500 CPU years optimizing these two parameters. For the radius of gyration retention, so I wanted to make sure that when you run fast design with a protein or protein interface, the complex or the system that you're designing, it doesn't change in volume. You want roughly it not to grow or shrink. The Rosetta score, when you're writing a sampling method, the score function that you're sampling is really low. So you really want to just improve the score often as priority number 1. And Rosetta also has some internal just metrics for sidechain packing quality and making sure, this is really more of a sanity check to make sure that what we're designing still looks like a reasonable protein. And all three of these traits were improved after fitting. And I'll dive in a little bit more later on what that means for interface design. In terms of what we're calling it, so Interface Design 2019, just for the talk, this will come back later because I'm going to show how it improves. It improved all three of these categories. There's also, those heat maps were slightly different for the top and bottom. So for the single chain heat map, I created Monomer Design 2019, which is now actually the Rosetta default. So now everybody who's running Rosetta is using this improvement for the past 6 months or so. And this is actually being tested in the lab by Hugh in the Baker Lab at the University of Washington. And he's not testing interfaces, so I didn't put much in this slide, but he's showing consistent improvement that proteins designed with Monomer Design 2019 are more stable. But that, there's really more to this story than just that. By all computational metrics, this was a big success. However, there's this sort of new sampling bias that was introduced. The protein compositions of what came out of fast design did not use amino acids in the same ratios that nature does. For example, fast design output might have more tryptophans than what you would see in natural proteins, or maybe not enough threonines. And this is where it gets a little technical. We decided that the reason for this is that when we ramp this repulsive weight, we need to update the baseline energies for each amino acid. Remember, near the beginning of the talk, each amino acid has a reference weight that makes it more reasonable to compare across amino acids when making mutations. And you can imagine that making the score function more forgiving in terms of atom density is going to impact larger side chains more than small ones. And this apples-to-apples comparison that we're striving for might be lost the more that we change the score function. So that's, fixable. We created just new reference weights for each intermediate phase of the score function that we use. And those new reference weights, when added to Interface Design 2019, we're calling Polar Design 2019. And I'm showing how it improves each amino acid distribution. So for each amino acid, I show in black how frequently it's seen in nature, so native. For this chart, these are all like protein-protein interfaces. And in gray for each cluster is what the old fast design, the legacy fast design used to give us. That's the old, before I touch anything, so that's really the control. Notice the spike in alanine. So that is really a sign of what I was mentioning before with the sampling bias, with the steric det and surplus, and the bias towards alanine. So that's a visualization to back me up. You take the legacy protocol and you introduce the new repulsive weights, those 2 degrees of freedom that we grid searched, and that gives you Interface Design 2019. And you can see the red flag that we saw, for tryptophan, like I mentioned. This Interface Design 2019 really increases how much you see. The same is true for, isoleucine or leucine. This light blue bar can deviate from the black one quite a bit. And in most cases, when we do this fix with Polar Design 2019, you see a reversion closer to native. Non-native distributions of amino acids are not inherently a problem, but they are a red flag. So we thought it was at least worth checking out. And by all of our computational metrics, there's no loss of design quality. So it seemed like a candidate to be the new standard. For the scope of today's talk, I'm going to be moving forward with Polar Design 2019. But in the bigger picture, these two are kind of competing to be the new standard, pending like actual experimental testing, not by me. And so just to summarize this fast design section, so fast design, flagship protocol for protein design. There's this sampling bias towards alanine and small proteins. This was a large hindrance with our problem with this interface hydrogen bond sampling problem. We removed this bias with Interface Design 2019, and then we then created Polar Design 2019 to better model native amino acid distributions. Now, I'm going to talk about a second protocol, but I'm going to do it much faster, because what I really want to get to is the end, where we benchmark, and we really show the improvements. Especially because, the second protocol, Monte Carlo HBNet, it was created with Scott Boykin in the Baker lab. He really created his own implementation back in 2016. It had computational resource problems, so he and I worked together for the second implementation published in 2018 to make something that could really handle problem sizes as large as an interface design problem, where we're going to have dozens of residue positions that need to be sampled, where his old system could really only handle, on the order of 6 positions. Monte Carlo HBNet designs hydrogen bond networks, and those are clusters of protein side chains that have this orchestrated manner of really hydrogen bonding with each other, leaving as few polar atoms without a hydrogen bonding partner as possible. In this example, we only have the one nitrogen down there without a partner, but everything else has this system of all satisfying these polar atoms in this manner. And HBNet just explicitly seeks out these side chain conformations and then puts these at the interface. In the big picture, when you design this interface, you have, each residue really has an unassigned state, but many candidate conformations for the side chain to be at that state. The idea is with HBNet, you assign a few of the states ahead of time. So you pick a few positions at the interface and assign states that are polar and are polar in a responsible way, where these polar atoms have hydrogen bonding partners. And then you allow fast design to come in as a second phase and really take care of the rest of the protein, but with the starting seed, knowing that you're really starting off on a good foot. The trade-off is that Monte Carlo HBNet only really considers hydrogen bonding score terms. It doesn't consider all the other parts of physics that we tend to model. Leonard-Jones, the repulsive weight that I've been talking about, electrostatics, and all these other terms. So there's a potential trade-off that you will dig yourself in a hole that fast design can't get you out of. So there's this art of, how far do you let hydrogen bond HBNet go? How much of the interface do you let it design, and how much do you then let fast design fill in the gaps? And we'll come back to that trade-off near the end of the talk. I'll quickly go through what this looks like in the computer. So if you imagine this toy example, we have these 2 protein chains, each one with 2 residues. We create this graph data structure where there's a graph node for each considered state at each position. And these nodes can span multiple amino acids. Mutations can be introduced in HBNet. You might have a few serine, threonine, and arginine all in the same residue position. And then you create edges between nodes that represent different positions but form hydrogen bonding partners. So these 2 nodes that have an edge, they both represent side chain conformations that form some sort of hydrogen bond. And the goal is to find some connected component in this graph where you have some set of nodes where you get all of these hydrogen bond interactions, leaving as few polar atoms without a hydrogen bonding partner as possible. The data in the graph actually keeps track of which atoms are interacting, so we can, in the graph data structure, you can figure out what fraction of these polar atoms are actually in hydrogen bonds, and you want to maximize that. There's also an extra set of edges. You don't want these side chains to take up the same space in 3-dimension. You don't want them to clash in space. So there are edges between conformations that are compatible. And so we need a click in that edge set, but just a connected component in this one. What this looks like in the protein, so we have this triangle of these 3 side chains that all have hydrogen bonds, that matches this triangle, and then this 4th one jutting out on the side. So this is when you're done sampling and bring it back to the protein, this is what you end up with. So that, this is the big, is all of this, did this help the problem? I mentioned that these benchmarks are computational. For the scope of my project, we're just checking to see if when you run these new sampling methods, do you solve this hydrogen bonding problem as far as you can tell on the computer? And then if these benchmarks are a success, then you move on to the lab. There are 4 protocols for benchmarking. So the control, which I had, which doesn't have my fingerprints on it at all, is legacy fast design. The first thing we introduce is the steric surplus fix, so interface design 2019. and then you move this sampling bias towards this non-natural amino acid distribution in Polar Design 2019. And then finally, you precede Polar Design 2019 with Monte Carlo HBNet in the manner that I mentioned before, where you only assign some of the states of the interface and then allow Polar Design to come in for the rest. I ran 2 benchmarks. I'm only going to talk about one, but I think it's worth mentioning the first one. So the first is, in my head, it's a wide and thin benchmark where I run these protocols on hundreds of different proteins, but only a few times. So it's noisy data, but we get a diverse sample set. And on top of that, and one of the reasons I'm not showing it today is that it's really more geared. If you think back to that timeline I showed at the beginning of all those Rosetta improvements, there were almost every year there's a major improvement in the Rosetta score function. And this benchmark wanted to test, how did protein design change as the score function changed? So that was one of the main purposes of this one. What I am talking today is instead of shallow and wide and shallow, this is narrow but deep. So there's only 6 protein-protein interfaces that I'm benchmarking, but for each of these protocols, I'm running Rosetta 1,000 times, which really matches what you would do in a production run. You might run Rosetta 1,000 times and then only take a small handful of designs and run with that in the lab. The metrics that I measure for each protocol are the interface polarity, what fraction of residues at the interface are polar, of the number of polar atoms you have at the interface, what fraction of them have hydrogen bonding partners. So unsatisfied polar atoms, you want to minimize. Unsatisfied means they don't have partners. And then Rosetta score. Like I said, when you create a sampling protocol, you really want the score to improve, sometimes above all. So just to walk through the benchmark, there are 6 proteins, A, B, C, D, E, F. So looking just at protein A first, the legacy protocol gives you, negative 3.21 Rosetta energy units per residue. That doesn't mean much right now. Only 16% of the residues at the interface are polar. You can compare this to in native, it's 52%. So that's a little bit of that's a problem when you start talking about solubility. And even though there aren't many polar residues, there's a large number of polar atoms without hydrogen bonding partners. So we want this number to be as close to 0 as possible, meaning every atom that's polar has a hydrogen bonding partner. And in native, that's 0.04. And we have almost triple that with the legacy protocol. With our first improvement, the biggest change is probably in the Rosetta score. So we get a much better Rosetta energy. But, the interface polarity goes up a bit, but not quite to native levels. And the hydrogen bond satisfaction actually gets worse, partially because we're introducing more polar atoms that can be unsatisfied. This is not normalized to be per polar atom. This is per residue. So with our next improvement with the amino acid distributions, there's a small hit in the Rosetta score, however, and no change in interface polarity. However, there is an improvement in hydrogen bond satisfaction. So with the same amount of polar residues at the interface, you can satisfy them better. And then finally, when you precede with HBNet, another small hit in Rosetta score, but it's still higher than where we started. Interface polarity is much closer to native. In fact, in protein A, it overshot native. And while doing so, it still lowers the number of polar atoms per residue that don't have hydrogen bonding partners. Right? It's easy to think that when this number shoots up, this will also shoot up. But this actually goes down, which means that we're handling our polar atoms responsibly. Just moving on to proteins B and C. So for A and B, kind of the winning combinations were this polar design with preceded by Monte Carlo HBNet. For C, HBNet actually made it worse. Made it just in all 3 columns. The Rosetta score got worse. The polarity, we're close enough to native. It's not clear that 43% is terrible. But this is worse. Introducing more polar atoms without hydrogen bonding partners. So in C, polar design is the winner, and it improves upon, for all of these, we find a winner that improves in all 3 columns. And then just moving on to the second set of proteins, which isn't really distinct from the first set, just to make room on the slide. We have another case where HBNet didn't make things any better, and then two cases where it's kind of a toss-up. I'm not enough of an expert to know how polar you really need to be. It's really, from our point of view, like this number is too low, but it's not obvious where you need to get to. Partially because that's a case-by-case. If you have a protein and you want it to bind and stick, you don't need to be as polar as your case where you want it to bind and unbind. So that's really more the role of the designer to choose where the cutoff is. But just to this is seen as a success that for all three of these metrics, we're able to improve upon the old protocol, consistently. So to summarize, in protein interface design, there are these two restrictions. You need to be polar, but you need to be polar with hydrogen bond sampling. You need hydrogen bonding partners. Rosetta, as of 2013, could not reliably meet both of these restrictions due to this insufficient sidechain sampling that Ben Strange has listed in his conclusion, and then the sampling bias that we found in fast design. And then today, we've been able to review improvements to this. We've been able to increase the polarity of interfaces, and not only without, it's one thing to increase the polarity of the interface and then keep the hydrogen bond dissatisfaction equal. That would still be a win in some sense. But we've actually been able to increase polarity in a sense that decreases the amount of unsatisfied hydrogen bonds. So it's really, just one of them alone with the other one fixed would be an improvement. But this is really two improvements, which are hard to do together. And then, improving the Rosetta score as a sampling method is always a win. We're at time. I would like to quickly do the acknowledgments.